All right, so today we are starting electrochemistry. All right, the beginning of this unit is on, the first two problems we're going to do is reviewing how to balance redox reactions. Way back in Unit 2, which was Chapter 4 in the textbook, you learned how to balance redox. At that point, I did not teach you how Chapter 4 did it because I don't like that method very much. Instead, I taught you how Chapter 18, we're in Chapter 18. Chapter 18 teaches it because I feel that that's better. And this way you didn't learn one method and then learn a different method now. We just use the same method all year long. And it's also the method that you learned if you took research chemistry with Mr. Smith last year. He taught you this exact same method that I'm reviewing today, which we've already done. We've already tested on it, all that stuff. But let's just review it because we haven't looked at it in a long time. All right, so looking at our first example, we have this reaction, and we need to know if it's in acidic or basic. This first one is in acidic. So, if you recall, what is our first step in balancing this redox reaction? Split them into the two half reactions. What would one of our half reactions look like? MnO4 minus Mn2 plus. And then our second half reaction looks like what? All right. And the states of matter aren't going to influence how we balance, so I'm going to leave them off to save space. All right. So now that we've split them into the two half reactions, we're going to balance what? Yep, balance everything except for oxygen and hydrogen, okay? And we're going to do each half reaction. In our first half reaction, Mn, manganese, is already balanced, so we don't have to do anything. In our second half reaction, carbon is not balanced, so how are we going to balance it? 2 in front of the CO2. So just normal coefficients balancing. All right, so now at this point, everything except for hydrogen and oxygen is balanced. So now we're going to go ahead and balance, which one of those do we balance first? Oxygen. And we balance oxygen by adding what substance? Water to the appropriate side. And then we balance the hydrogens by adding, H pluses. Okay, so in our first half reaction, we need to balance out the oxygen. I need how many waters? 4 waters on which side? The right side. And then that gave me 8 hydrogens. So what am I going to add to the left to balance out the hydrogen? 8 H pluses. And now for my second half reaction, oxygen is already balanced because we have 4 on the left and 4 on the right. I just need to balance out the hydrogens. So how many am I going to add into which side? 2 to the right. And now that we have all of the elements balanced, we now need to worry about the charge. We need to worry about the charge. And we're going to do that. We're going to balance the charge by adding electrons to the appropriate side. Again, we do each half reaction individually. So, for my first half reaction, what is my overall charge on the left? +7. I'm going to put that in parentheses underneath because we have +8 minus 1, so +7. What's the overall charge on the right? +2. You are going to end up adding electrons to the more positive side because remember, electrons are negative. So when you add electrons, you're bringing down the charge of whatever side you're adding them to. So we're going to have to add electrons to the left side to bring down that +7 charge. So how many do I add to go 7 to 2? 5. Yay, we can do mental math. So I'm going to have to add 5 electrons to the left side for that first half reaction. And now for my second half reaction, a kind of a check, When you figure out your overall charges, you should be adding electrons to the opposite sides for each half reaction, otherwise you've done something wrong. So for this second half reaction, what's my overall charge on the left? 0. And on the right? +2. So yes, I'm adding electrons to the right because the right side is more positive. So how many electrons do I need to add to the right? 2. All right, now that I've balanced the charge for each half reaction, we need to make the charges, or the electrons, match for each half reaction. The electrons that are being lost by one half reaction need to be the same number gained by the other half. So, how do I make the electrons equal? Yep, we're going to find the least common multiple between 5 and 2, which is 10. So this entire top reaction, we're going to multiply all the coefficients by 2, not +2, times 2. And the second half reaction, we're going to multiply everything by 5. So that gives me, instead of 5 electrons, I'm going to have 10. What's 8 times 2? 16, and I'm going to have 2 of these and 2 of these, and 4 times 2 is 8. And then here, I'm going to have 5 of these. 2 times 5 is 10 of each of these. Okay? And now I can recombine my reactions, canceling out things that are going to cancel. For example, the electrons will cancel. I have 10 electrons here and 10 electrons here that are going to cancel out. Also, I have 16 H pluses on the left and 10 on the right, so my net will be 6 H pluses on the left. Okay? Nothing else is going to cancel out. And if you wanted to, you could add back in the states of matter. Remember, all ions are aqueous. Everything else, you can just look back at the original state of matter in the problem. Water is liquid. Okay, and that's my final answer. Because this was an acidic, we're going to leave it as H+. Questions on that? Nice little review from Unit 2. I know it's been a while since we did that. All right. Are we good there? Yeah. Awesome. So my next problem, actually, hold on. Before we move on, the whole point of this is not just to balance redox. We're actually going to be eventually discussing like what's happening with the electrons, and we're going to talk about how we can calculate the overall electron potential of this, basically how much electricity we can get out of this reaction. So to review reduction and oxidation, which one of these half reactions is my reduction half reaction? Ooh, challenge question. Did you say the one on the left? Why is the bottom one reduction? I'll give you a hint. The bottom was not the reduction half reaction. Yeah, the bottom one is the oxidation half because you're losing electrons. Remember, oxidation is losing, oil rig. So when you lose electrons, when electrons are a product, it's oxidation. When you're gaining electrons, reduction is gaining. When the electrons are a reactant, it's reduction. Okay? And we'll go over those some more in just a little bit, but the oxidation half and the reduction half, that's coming up. Okay? We're going to be utilizing that in a little while. Right now, we're just reviewing how to balance. Okay? All right. My next example problem is a similar one. The difference is that it is in basic solution as opposed to acidic. And in your problems handout, the Br minus, that's the product, the minus sign kind of blended with the R. So I just want to point out, like, I ended up adding a space on my screen here just to make it really clear that there's a minus sign there. So just be aware that, I don't know why I did that. And I think your homework might have some like that where it kind of blended, so just be aware, okay? So why don't you guys go through, remember, when you balance something in basic, the original steps are all the same. You balance it as if it were an acidic, and at the end you do something different. So get this balanced as if it were in acidic, and then we'll come back together and go over how to make it basic. All right, so now that you've had a chance to balance this as if it were an acidic, let me get to that point with you guys, and then we'll talk about what to do since it is in basic. So just like before, I'm just going to go through this quickly. We're going to split it into the two half reactions. We don't have anything other than oxygen and hydrogen that isn't balanced. Everything but oxygen and hydrogen is already balanced. So I can just start by adding the waters and the hydrogens where needed. So for the first half reaction, I'm going to add 3 waters to the right. And then that means I need 6 H pluses on the left to balance that out. For the second half reaction, we have no oxygen or hydrogen, so we don't need to do anything more there. So now we go to electrons. So I'll do the second one first because that's easier. +2 versus +3, we're going to need 1 electron on the right to balance that out. And then for the first half reaction, we have an overall of +5 here, and we have an overall of -1 here. So that means I'm going to need 6 electrons on the left, because I have to go from 5 to -1. Okay? Now, before I move on, which one of these is my oxidation half? The second one. This is my oxidation half reaction. Therefore, my first one is my reduction half. All right. So now, in order to make the electrons the same, I'm going to have to multiply this second one by 6. Why do I keep writing a plus sign? Times 6. So that means I have 6, 6, and 6. What? The little thing in the corner, what? What? It's still recording. When I'm paused, there's a box. I think there's supposed to be a box while I'm recording, but I can't figure out how to make it stay up there. So, it's still recording, and I still have a blue light, so I'm good. All right, so now that I've done that, I'm going to recombine, canceling out things that cancel. So my electrons are going to cancel. Nothing else cancels, though. So I have 6H plus BrO3 minus plus 6Fe2 plus goes to Br minus plus 3H2O plus 6Fe3 plus. All right, so now in order to make this basic, we are going to add what type of substance? OH, hydroxide. We're going to add as many hydroxides as we have H pluses, but we're going to have to add that to both sides of the equation. It's like in math. Whatever you do to one side, you have to do it to the other. All right, so we're going to add 6 hydroxides to both sides. All right, that creates how many waters? 6 waters. All right, which will cancel with some of the waters on the right. Okay. So that's going to be a net of 3 waters on the left. So my overall equation after we've made it basic is this. Okay. And again, you can go back through and fill in the states of matter. All of my ions are aqueous. And water is a liquid. Okay? So that's how you balance in basic. Now, I don't remember if the textbook goes through that or not. There is actually a set of rules for basic where instead of adding H pluses and H2Os at the beginning, you're adding H2Os and hydroxides at the beginning, but I just find it so much easier to do it this way. Okay? Questions? All right, so now we're going to jump into the actual content for this unit, which is galvanic cells and electrochemistry and all that stuff. Today we're going to talk about galvanic cells, and then in 2 classes we're going to go into something called the Nernst equation and how to actually calculate like how many amps you can get, how many like amps of power, or like how long the cell would run. You'll see. It's all stoichiometry. You'll see. All right? Okay. So I asked you to turn in your textbook to page 845. Wasn't that the page number? Yes. So this chart, I put this in your guided notes, but then I realized on Friday as I was about to go over this with 6 block that in the guided notes it didn't copy over the best. So I was like, let's just access it, in the textbook. If you're at home and you don't have your textbook on you, or if maybe you're in study hall or something, you can find this chart online. The guided notes are posted on Vision, and the chart online is fine. It's just when it printed and copied, a lot of the charges were really light, and so it's hard to see. All right, let's talk about this table first before we get into doing more practice problems. What is the title of this table? Okay. Standard reduction potentials for common substances. Standard what potentials? Reduction potentials. Look at all of what's in this table? What are these things called? Half reactions. They're all half reactions. They're all half reactions. What do you notice about all of those half reactions? They're all reduction half reactions. They are all written as a reduction equation. Okay? That's what this table is. It's basically telling you how much voltage, what voltage you can get from each of those half reactions compared to this equation. Notice how it's kind of outlined? The hydrogen reduction equation, and it has a voltage of 0. That was set as the standard. Okay, so all of these are in comparison to the reduction potential that we get from hydrogen. So, what this means, for example, the reduction of fluorine will give you 2.87 volts more than the reduction of hydrogen because it has a positive 2.87 voltage. The reduction of, say, lithium, way down here, will give you a voltage of 3.05 less than hydrogen gives you. So that's why some of them are positive and some of them are negative. And hydrogen was set as the standard. We could have set any of these as the standard and compared it and found the voltage. Actually, in a few classes, you're going to do a lab like that, where you're not going to do the 50 that are on here, you're going to do like 5, where you're going to set up galvanic cells, comparing it to a standard. We're going to do zinc as our standard instead, and you're going to measure the potential based compared to zinc, and so you'll know like, oh, well, this one I'm getting a voltage of, like 1.2 more than I got for zinc. Okay? So, like I said, all of these are reduction equations. All of these are compared to hydrogen. Okay? Now, this chart is in the back of your textbook under the appendix as well. The only difference, the one difference in the appendix chart versus this one is the one in the appendix didn't outline the hydrogen reduction equation. I don't know why, but yeah, that's the only difference. All right, so now let's talk about how we're actually going to use this. Well, we're going to do a problem first. Which of the following species is the strongest oxidizing agent? And then we're given 3 substances. MnO4 minus in acidic solution, Br2, or Ca2+. Well, what it means by oxidizing agent, that's not something we've defined before, but it is on the first page of your guided notes. That definition's there. What this really means, the oxidizing agent is the substance that is being reduced, okay? The reduction agent is the reducing agent is the substance that is being oxidized. So really, what this question is asking is which of these substances, instead of saying the strongest oxidizing agent, let's say is the most apt to be reduced. Which one of these is the most apt to be reduced? So what I want you to do, so we're comparing MnO4 minus, and this has to be in acidic, Br2, and Ca2 plus. Take a moment to look at, find in the chart, I'll give you guys a chance to look at the chart in your textbook, find those reduction potentials for each of those. All right, so now that you've taken a moment to find these reduction potentials, I'm actually going to start with calcium. What is calcium's standard reduction potential from the chart? Negative 2.76, and that is volts. What is bromine's? 1.09 volts. And what is MnO4 minus's? Oh, I'm hearing different values. Well, let's look at the chart. Let's try to figure out which one it is. Because I heard 0.56, I heard 1 point something. So MnO4 minus is actually on this chart 3 times as a reduction equation. It's right here, and right here. Now, 2 of these 3 are in acidic solution. 1 of them is not. Which 2 are in acidic solutions? The first 2, because it has H plus in the reduction equation. That third one doesn't specify if it's in acidic or in basic, so therefore you can, because this problem specifically said MnO4 in acidic, we can only look at the first or the second. Now, without any other information, we actually don't know which one of these we should be looking at. Which one of these. So we can use either one. It's fine because it's not like the bromine or the calcium's in between. So it's okay. So we have 1.68 or 1.51. The one you cannot use is the 0.56 because it's not specified as being in acidic.
If you put MnO4 minus in acidic solution, can you predict which one it's going to?
We would need to know what else it is reacting with. By just the 1/2 reaction, we don't know. We would need to know what the other half reaction is, like what oxidation would be occurring. Was that your question, Sim? How would you figure it out? Yeah, so you would need to either know what it, so if you look here at this one, the products are different. One of them, the MnO4 minus, is going to MnO2, and the other one is going to Mn2 plus. So typically, you're actually going to be given the whole equation, and then you would need to know, okay, if I'm forming MnO2, I'm going to use this voltage, the 1.68. If I'm forming Mn2 plus, I'm going to use the other one. But we don't know which one this is being reduced to, so again, it's okay, whichever one you want to use. All right, so now, to answer the question, which one's most apt to be reduced, the answer is MnO4 minus. And the reason why is because it has the largest reduction potential, meaning it is most likely to be reduced. Between these three things, MnO4 minus has the highest reduction potential, therefore it's going to be reduced compared to the other ones. Because it has the of these three, calcium is most likely to be oxidized because it has the lowest reduction potential. So most likely, like if we had a reaction between MnO4 minus and Ca2 plus in acidic solutions, the Ca2 plus would actually be a product. It would be oxidized to that from calcium. Okay? And that's what we're going to be looking at. All right. Are we ready to move on to the next one? And actually learning how to calculate E of the cell and what that means? All right. So this one. Will aluminum displace Cu2 plus ion from an aqueous solution of CuNO3 So I'm going to start off by writing my reaction. Okay? So aluminum, how do I write that? Al. That is reacting with what? Calcium nitrate. What type of reaction is this? Single replacement, which is oftentimes called single displacement, because what's happening in a single displacement or replacement reaction is a metal is displacing the ion. All right? And there's actually redox occurring here. What are my products? Cu and aluminum nitrate, which is AlNO3 3. And this is not Cu2 plus because it's going to be the metal. Okay? Now let's go ahead and change this to a net ionic equation. Instead of leaving the NO3s, let's get rid of them, right? So to save space, I'm just going to erase the NO3s. And then write in the charges that those things had. So the Cu here had a +2 charge, or 2 plus. I'll be consistent. And this one was Al3 plus. So really, what this question is asking is this reaction going to occur? And in order to answer that, we're going to look at the reduction potentials of the two half reactions and figure out, overall, do we have a flow of electrons or not? Okay? So let's go through, and just like before, this one's easier though because there's no oxygen or hydrogen. Let's split this into the two half reactions. What are the two half reactions? Al to Al3 plus and Cu2 plus to Cu. Go ahead and balance those two half reactions. The only thing you have to do is add the electrons because there's no oxygen or hydrogen. Okay, so, actually I meant to pause while I was waiting for you guys, but I forgot. All right, so where do the electrons go for the first half reaction? To the right side. How many are we going to add? 3. And then what about the second half reaction? 2. We're not going to worry about going any further than that for right now, okay? We're not going to worry about making the electrons match or anything yet. How do you describe or characterize that first half reaction? That is oxidation. Therefore, my second half reaction is reduction. So, look at the chart on page 845. Find the reduction potential for this Cu2 plus going down to Cu. What is it? Really?
Wait, no, that's okay, 0.16. I was thinking C plus 1.
I don't have either of those. I have 0.34. So Cu2 plus to Cu, which is here. Yeah, because there's Cu2 plus to Cu plus. There's Cu plus to Cu down here. So there's multiple on here, but you have to find the one that's Cu2 plus going down to Cu, which is 0.34. So my E, the electron potential, that's what, now the textbook does that weird cursive E, and I don't like having to change the font when I'm typing, and so I just always write just a regular capital E. The E of that is 0.34 volts. Now, if you try to find the aluminum one, what? So if you try to find the aluminum one, we don't have the equation of aluminum to aluminum 3 plus because this equation here is oxidation, and the chart are all reduction potentials. So when you look at the chart, you have to flip the equation around in your head and find aluminum 3 plus going down to aluminum, which is right here, negative 1.66. So this one, the E, it's negative 1.66 for the reversed equation. So what do we do to the sign? Positive. Make it positive. So this would be positive 1.66 volts. It was negative 1.66 volts for reduction, but because this was oxidation, we have to flip it. Okay? So to find the E of the entire cell, we're going to go through and let's balance out the equation. In order to balance that out, what do we need to do? Top needs to be multiplied by 2, and the bottom one needs to be multiplied by 3. But the beauty of this, and this is where students most often make mistakes, when you're balancing the half reactions out and you're recombining, when you multiply the equation by coefficients, you don't change the E, the voltage. You don't multiply the cell or the electron potential for those two things. Okay, you leave it as is. All right. So my overall equation is going to be 2Al plus 3Cu2 plus going to 2Al3 plus 3Cu. Now to find the E of the cell, that is E of the oxidation half reaction plus E of the reduction half reaction. So my E of the cell is going to be 1.66 plus 0.34, which is 2.00. And since that is positive, that means that the reaction is favorable in the forward direction. That means that this reaction, as written, aluminum plus Cu2 plus, will occur because we will receive electricity from the, like, electrons will flow, meaning that they will transfer from the aluminum to the copper. Okay, means there will, and there's a positive flow of electrons, means it's good. All right, and yes, this we will, in 2 classes, we will relate this to delta G. Okay, but yeah, so a positive E cell, that's good. If this answer was negative, that means that the reaction would not occur as written, and actually the reverse reaction would occur. Okay? All right. So now, any questions there? Yeah.
Isn't it asking if, like, the ion would be displaced, but isn't the ion on the reactive side?
Yeah.
So
In this aluminum displaced the copper ion.
okay.
Yeah, that's what.
Okay.
Yeah. Yep. Okay. Oops, too far. So this one is just like the last one. So even though I said I was going to remove duplicate stuff, I originally this packet had a lot more duplication. Okay. So what I want you to do is you guys can work on this one, go through this. You're going to go all the way through and find the E of the cell, figure out if the reaction will occur, and then we'll check back in. All right, so you've had time to do this one. So what are my 2 half reactions? PB going to PB2 plus. Where are the electrons in this one? On the right side. How many electrons? 2. All right, and then my second half reaction is? All right. What does that second half reaction look like balanced? 2 in front of the Cl minus. And 2 electrons on the left. All right. Which one of these, what is my first half reaction? Oxidation. And my second half reaction is? Reduction. All right, wonderful. So my overall equation, we don't have to worry about multiplying anything because we had same number of electrons being lost as being gained. So my overall, like it's our, like the only thing we really did was we added the 2 in front of the Cl minus. All right. So if you look at the chart, what is E for the first half reaction? 0.13 volts. It was negative on the chart. Why did we flip it? Because this is oxidation. And then E for my reduction half reaction is what? 1 point what? I have 1.36. I have 1.36. You guys grabbed this one instead of this one. That was just you didn't line up the chart well. So what is my E of the cell? 1.49 volts. So will this reaction occur? Yep. All right. The way that the textbook has you calculate E of the cell is they actually don't have you flip the sign for the oxidation half reaction. I don't like that because what they want you to do is always do the reduction half minus the oxidation half, but only using reduction potentials. And I find that sometimes difficult to remember which one to subtract from which. This way, if you just flip it so that it matches exactly what's going on in the reaction, just add them together. Okay? All right. The last little bit we're going to talk about is how to actually sketch a galvanic cell. All right, so looking at this one, it's gonna take, like, this is going to be the longest problem we're going to do because there's a lot we're gonna talk about, okay? Let me get the skeleton of a galvanic cell out there, and then we'll start labeling it with the different parts and the different substances. So all galvanic cells consist of two containers that have the electrodes sitting in it. Now, just so that you're aware, this is how much space I took up for the last equation. If you look on my page, the last problem, so just budget your paper wisely, okay? I took up pretty much the entire space. All right, and then there is some sort of wire connected to the two electrodes, okay? I'm going to be adding to this other things that we need in order to make this cell actually work and operate. But let's start with what we have here. These two, like, rectangular shapes that I drew are the electrodes. And these will be made of the metals that are in your reaction, okay? Or if, like, in the last one we had Cl2 going to Cl minus, what we would have there instead is like a platinum electrode, and the Cl2 would be in the solution, okay? We'd have some sort of unreactive metal like platinum or palladium or something like that. But here, my two electrodes are going to be made of cobalt and copper because those are my two metals that I am using. Now, for right now, it doesn't matter which one you put on the left versus the right. For a galvanic cell, it doesn't matter. You just need to know, you need to eventually figure out which one's going through oxidation, which one's going through reduction. So, which one do you want to put on the left? I heard cobalt first. Actually, that's the only one I heard. So that means this metal is made of cobalt, and therefore this metal is made of copper. Okay? Now, these metals are sitting in a solution that contains the same ion as the metal. Okay? So that means that the cobalt electrode is going to be sitting in a solution that contains 1 molar I did that last time too. 1 molar cobalt ion. And the anion would be something like a nitrate or a chloride, something that's not going to precipitate out. Okay, something that would be in ion form. My copper electrode is going to be sitting in a solution that contains 1 molar copper ions. From our full equation, I'm going to write off to the side the two half reactions based on the equation as written. So my first half reaction is going to be what? CO to CO plus 2. Where did the electrons go there? On the right. And that's going to be 2 electrons. And my second half reaction is? Yep, and my electrons are on the left there. Okay? Which one of these is oxidation and which one's reduction? This first one's oxidation, the second one is reduction. Good. So, at this electrode, at the cobalt electrode, we have oxidation occurring. At the copper electrode, we have reduction occurring. The electrode where oxidation is occurring is called the anode. And the electrode where reduction is occurring is called the cathode. And now some ways to remember that oxidation occurs at the anode, reduction occurs at the cathode. One of the ways is a little saying that's red cat and an ox. Red cat and anox, or what type of letters do anode and oxidation start with? Vowels. And what type of letters do reduction and cathode start with? Consonants. So vowels go together, consonants go together. This way you don't have to remember which animal is red. Is it the cat or the ox? All right. So I like vowels and consonants better, but if you're more the type of red cat and an ox, red cat and an ox, just remember it's not red, ox, and a cat. And now that I've said that, you're going to be like, wait, which animal's red? All right, so vowels together, consonants together. All right, so we've taken care of, we've labeled the anode and cathode. So we've taken care of the first little bit. We know what the anode and cathode electrode materials are. We've already kind of figured out the half reaction at each electrode, but there's this thing called the salt bridge. And then the direction of electron flow that we're going to talk about. So right now, if I set this up, electrons will not flow. And the reason why is we do not have a complete circuit. So think about physics, so those of you who've taken it, and also you know from like elementary school and middle school, like, you know, when you have a circuit, like a series and stuff like that, you have to complete it, you have to close the circuit in order for electricity to flow. Similar concept here. In order to close the circuit, we need what is called a salt bridge, okay? And my salt bridge is going to connect my anode and cathode solutions, okay? When you do your lab in a few classes, you're going to have a salt bridge. It's just going to be a piece of filter paper, like a strip of it, that's been soaked in typically KNO3. It's a great solution, and it'll be a solution of KNO3. So in here we have KNO3 and its solutions, so we're going to have K plus and NO3 minus. The book talks about using a porous disc as well. That's, I think, more of what batteries use. So, but there needs to be some sort of salt that won't precipitate out with either of these solutions in our electrodes. You know, that's why KNO3 is a great one, because remember, all nitrates are soluble, alkali metals are soluble, so it'll be good. So now this will complete the circuit. We'll talk about in a moment what happens with the ions in the salt bridge. Let's talk about electron flow. Electrons flow from the anode to the cathode. So think alphabetical order, or A to C. All right, so that means that the electrons are going from the anode to the cathode along this wire that I drew up here. So my electrons are flowing from the anode to the cathode. In order to balance out the charge, if we didn't have the salt bridge, we would end up with a buildup of charge. If the electrons actually flowed, we'd end up with a buildup of charge on my cathode. So the salt bridge is there to balance it out. Okay? So this is my salt bridge. I forgot to label that before. In my salt bridge, the anions in the salt bridge, so the nitrate, will go towards the anode, and the cations go towards the cathode. That should be easy to remember. So that means that going into the solution of my anode, I'm going to have NO3 minus ions coming from my salt bridge. And going into my solution of the cathode, I'm going to have K plus ions going into there to balance it out. Because otherwise we'd have a buildup of positive charge on my anode and negative on my cathode. So those ions are there to keep it balanced and keep it overall neutral. I'll do lighter blue. So let's talk a little bit more about what's happening at each of these electrodes. So at the anode, we have oxidation occurring. We have this half reaction occurring. That means that the cobalt electrode, that actual metal piece, those atoms are being converted into cobalt 2 plus ions. So what is going to happen to the mass over time? What's going to happen to the mass of that piece of cobalt? It is going to decrease because those atoms are being converted into the ions. So that's going to lose mass. Now at my cathode, so the anode will always lose mass and the cathode will gain mass. That's because at the cathode reduction is occurring, we have Cu2 plus going to Cu. So that means the ions in this solution here are being converted into the atom form, and so making more copper atoms. So this is going to gain mass. Okay? So the anode always loses mass, the cathode always gains mass. And another way to remember that, oxidation is losing, not only is it losing electrons, but that solid metal is going to be losing mass. Reduction is gaining, not only is it gaining electrons, but the electrode is gaining mass. The red cat gets fat, and that rhymes, and hopefully that will help you remember that the cat is red, and the ox is just there. Actually, I think, wasn't that in the notes? The red cat gets fat? Oh, okay. Well, okay. I feel like I've heard that before, but maybe not. It was good, though. All right. The last little thing we're going to do is I'm going to write something called line notation. And I'm going to I'm blocking off a space for it. The one thing we're not doing in this question is we're not going to calculate E of the cell. And that is because for some reason, this cobalt equation is not on the chart at all. I don't know why it's not on there. I guess that one is not common. So it's not on there. So we're not going to deal with that. Don't worry, if I'm going to ask you to calculate the E of the cell, the things will be on the chart, or I will give them to you, okay? So line notation is like a shorthand for a galvanic cell. The guided notes in the textbook go through it. You always, this one, the line notation, the anode will always be on the left. It goes anode to cathode, okay? So we're actually going to draw it in the way that our galvanic cell is drawn. But just be aware that you will have some problems where you have a galvanic cell and the anode's on the right. Just you have to look, you use context clues and stuff like that. So our line notation, it's always going to be the anode's metal, or the material, and then there's a line that separates the anode from the anode's ion, and you always put the concentration. And then a double line to represent the salt bridge or porous disk. And then the cathode's ion with concentration. And then another line, and then the cathode's material. So as you read left to right, it's actually showing you what's happening. So we have cobalt going to cobalt 2 plus. That's oxidation. That's the anode. And then we have Cu2 plus, copper 2 plus, going down to Cu. That's reduction. That's my cathode. So like what's happening, you just read that left to right. So a single line represents a phase boundary, between the two substances of that electrode. A double line represents a porous disk or salt bridge, separating the anode from the cathode. Okay? Questions on that? Yes?
Maybe like a weird question, but how do you know if the
They will always flow from the anode to the cathode. And also remember, oxidation at the anode, we have oxidation occurring, and that cobalt is losing electrons. It's going to the anode, which is gaining the electrons. So that's why it has to flow that way. All right? Okay, so that is it for today.